All right, thanks, Tom. I will dive right in. So the first few slides here are going to be probably very obvious information to a lot of you, but it's important, motivating stuff here. So we're talking about solving PDEs, and anytime you solve a PDE, you lay down some kind of discretization, and just by doing that, you incur some sort of discretization error, right? This is something we all know if we work with PDEs. And then when you go and solve your algebraic system that you get out of putting down this discretization, you really should only be worried about solving this algebraic system to the level of discretization accuracy. Any further accuracy you get out of the algebraic system is sort of wasted effort, right? So what we're going to be talking about for this talk is efficient ways and efficient algorithms for attaining discretization accuracy. One such algorithm that you've probably heard of is just sort of classical full multigrid, right? And when I say full multigrid or FMG for the remainder of this talk, I'm talking about the geometric sort of classical method. And an FMG cycle looks something like this. We start out on the coarsest level of our multigrid hierarchy and work our way up to the fine grid. And this thing, of course, attains discretization accuracy in a single one of these cycles, for at least for second-order elliptic PDEs and things like that. And so this is, and this cycle takes order n computational costs. So that's great news. Makes this a really nice algorithm if you have a geometric hierarchy. So what if you don't have a geometric hierarchy? So as you know, the problem geometry can get real complicated in some cases, or sometimes it's simply unavailable. Somebody just hands you a matrix and says, go off and solve this for me. So what do we do in such a case? We use algebraic multigrid. AMG generates a multigrid hierarchy based only on the discrete operators. So we don't care about problem geometry for AMG. That makes AMG very convenient, makes it a widely used solver and preconditioner. And most of the time when people talk about using AMG, they're talking about using V cycles. So we're talking about a different cycle structure than FMG. And the thing about V cycles is that in general, as your problem size scales up, you need more and more of these V cycles to attain the level of discretization accuracy. So it's not quite as nice and scalable as this geometric FMG cycle where it just always takes one of these order n guys and you've got your discretization accurate solution. Here you generally need more and more of these V cycles. So one natural question you might ask, a question that I asked, is what about just applying an FMG type of cycle to an AMG hierarchy? Would that work? Can we recover discretization accuracy nicely through this kind of method? And so that's what we're going to investigate. And to do so, we're going to use a simple model problem, multigridder's favorite model problem, Poisson on a square. We're going to discretize with bilinear finite elements, zero boundary conditions, and plug in a nice manufactured solution so that we can actually measure discretization accuracy directly. And when we run FMG versus a full algebraic multigrid, so an FMG cycle applied to an AMG hierarchy on this simple model problem, we obtain the following results. So I've plotted on the vertical axis a relative error in L2 norm. And then the horizontal axis is sort of additional fine grid V cycles after you get your initial guess on the fine grid. So to make that absolutely clear, iteration 0 is sort of when you first hit your fine grid in your FMG cycle, and then additional V cycles are those iteration counts. So we really say a full FMG cycle would be done on iteration 1 here. So you can see FMG is as you scale up problem size, just crushing this thing to discretization accuracy, no problem, as you would expect. But FAMG, you can see it's taking more and more fine grid V cycles to get down to that level of discretization accuracy. So obviously just the naive approach of taking an AMG hierarchy out of the box and slapping a full multigrid cycle on it is not performing as one might hope. So the question is why? Why would this happen? So to look at that, a natural question is, why does FMG work? So you can go through a proof that shows that a single FMG cycle should converge to discretization accuracy. And one important step in this proof, sort of the crux, has to deal with interpolation error. And what do I mean by interpolation error? I mean, if you solve on your coarse grid and get a coarse grid solution U2H and project it up to a fine grid, what is the difference between those two solutions? So UH there is the exact algebraic solutions, exact solutions to your algebraic systems. So interpolation error should scale on each level of your multigrid hierarchy like the level, like your discretization accuracy scales. So how does AMG interpolation error look? And the answer is it looks bad. So what you see here is, for our particular problem, we expect an order H scaling of this interpolation error. And if you look at a geometrically generated multigrid hierarchy, it's scaling exactly like order H, like you would, like you want. But for AMG, it's looking pretty much constant, which is bad news. We're never going to get this nice FMG type convergence out of an algebraic hierarchy if interpolation error is flat like that. So let's look at how might we improve AMG interpolation. So to get a better sense of sort of what's going on here, I plotted the interpolation error over the domain to see sort of where are we screwing up here. So the top row here is the interpolation error you get from a geometric hierarchy. And we can see that this is fairly small in magnitude and very oscillatory. This is exactly the type of error that's just totally crushed by additional V cycles, right? This is the kind of error that we can easily remove. But if you look at the error for an AMG hierarchy, you can see we have these sort of nasty jumps near the boundary of the domain, and that sort of pollutes everything across the middle here. We get this big smooth mode sticking around, and that's the kind of error that takes longer to remove with V cycles, right? So we want to try and get rid of this type of discrepancy at the boundary in some way for AMG. So the way that you normally would calculate AMG interpolation weights is through this formula here. If you haven't seen this formula in a while, don't stare too hard at it. But basically this is just standard Rugi-Steuben calculation of interpolation weights. And it's based on the entries in your matrix and strength of connection and that kind of thing. And the important takeaways here are that this formula implicitly puts the constant vector in the range of interpolation. We care about putting smooth vectors in the range of interpolation. That's what we really would like to accomplish. And so AMG sort of assumes the constant is a nice smooth guy for lots of problems. Let's make sure we put that in the range of interpolation. However, near the boundary of your domain, if you're using these zero Dirichlet boundary conditions the way we are, the constant is not necessarily what you want there, right? So to remedy that, you can modify this formula in the following way. So we put in these little x guys here. These are components of some arbitrary vector x that we'd like to fit. So if you just plug in 1 for x, you recover standard AMG interpolation weights. And we're curious what might be a better choice for x. And recall that this choice for x should be some kind of smooth near null space component for our operator. Well, one thing we can do for our model problem is just plug in the lowest eigenvector, right? Poisson is well understood. We actually know what that is. It's just a sign hump, right? So if you plug that in, unsurprisingly, this works very well. We recover this order H scaling of the interpolation error, and we recover as you scale up problem size, convergence to discretization accuracy in a single cycle for FAMG. So that's great. We're done, right? Not so much. We sort of cheated here, right? We know the eigenvector that we're looking for, and we just plug it in. This kind of information is not usually available for more difficult problems, right? And you can try and find these guys adaptively, but that starts to get very expensive. And our focus is really to try and find some cheap fix to AMG interpolation to sort of recover this nice properties that we get out of the geometric hierarchies. So you could go full adaptive, but that may be sort of overkill, right? So what's another idea? Another idea is to focus on local null space vectors. Rather than try and go after global near null space guys, what about local null space? And what I mean by local null space is for every row in your discrete operator, every row in your matrix, you can select interpolation weights or select values such that that row produces 0 on the right-hand side, right? So for our Laplace operator, it has row sum 0 everywhere except for at the boundary of the domain, right? So if you just plug in a constant, that works for this. The constant fits these local null spaces, but not near the boundary. So what we can do is in the interior of the domain, where the constant is in the local null space, leave that alone. Just generate your interpolation weights normally. But around the boundary where you have row sum non-zero, we're going to plug in something else for that vector x that I showed you earlier. We're going to plug in a constant that's been smoothed a little bit. And if we do that, again, we see we get much better interpolation error scaling. We get much better convergence to discretization accuracy. One caveat for this method is I noticed that as you scale up problem size, you tend to need more and more of these smoothing iterations on each level to get the performance you want. More and more of the smoothing of the constant. So that sort of makes this method a little iffy. So let's go in a totally different direction. We tried several things to fix up AMG interpolation, and this is another thing that we tried. And that's to use some geometric data. So we're no longer going to be a purely algebraic method. We're going to use the locations of the degrees of freedom over the domain. And we're going to use that information to actually explicitly try to fit linear vectors. So fit the constant, fit a linear vector in x, and fit a linear vector in y. You can do that with I used just a constrained minimization there. And if you do that, again, you recover nice scaling of the interpolation error, and you recover nice convergence to discretization accuracy. So this, again, like I said, is no longer purely algebraic, but getting things like the locations of degrees of freedom is usually readily available in finite element codes and things like this. So this is not a big deal in terms of reducing the algebraicness of the method. So for my last few minutes here, I'm going to switch gears a bit and talk about coarsening schemes. So far I've been really focusing on what can we do to improve AMG interpolation to recover discretization accuracy. And I haven't talked anything about what these coarse grids actually look like. And one reason for that is for our nice model problem, standard AMG coarsening, so the standard Rugi-Subin coloring algorithm, produces the exact same coarse grids that you would get from geometric coarsening. So we sort of removed that from our list of concerns and just focused on interpolation. Well, what if you do something different? What if you use some variant of the coloring algorithm or some other algorithm altogether which produces non-geometric coarse grids? we tried that, and it does in fact have an impact. So we see here, this is again using this last interpolation method that I talked about, fitting explicitly the constant and linear vectors. And you can see that on the first couple of levels of your hierarchy, your interpolation error looks nice, but then as you go coarser and coarser, as your coarse grids get sort of more and more mucked up and farther away from what you get from geometric coarsening, you start to lose nice scaling of the interpolation error. And again, this is not so bad that we lost convergence to discretization accuracy, but it is sort of a red flag that if we're going to try and come up with an algebraic method that behaves like FMG, we're going to have to really pay attention to how we select coarse grids. So to wrap up, what did we learn? We learned that if you just throw an FMG cycle on a standard AMG hierarchy out of the box, that it's not going to behave nicely like you might hope, right? You need to do something to modify AMG interpolation to recover the nice properties that allow full multigrid to behave as it does. And we suggested a couple of different ideas of how you might go about that. And one thing that we didn't touch on too much is selection of coarse grids. That's something we'd like to look at in the future for how to make sure we select these things in a way that also ensures nice properties for interpolation error. And that's it.
Questions for Wayne? John?
Yeah, you said on the, you use kind of irregular coarsening or something.
Mm-hmm.
For the first few levels, you find it, second ones, and so on, and things look nice, and so on, coarser levels, and starts going up.
Yeah, it's a little hard to,
Yeah.
these are a little hard to see, I realize, but you can start to see things going a little bit awry. This is the coloring algorithm that was just sort of laying around in Toby's old code, which is what I was using. And I never did quite figure out exactly what variant he was using. But it basically sort of, you get this sort of offset behavior. C points are sort of shifted, and that sort of exacerbates as you go down the levels. You start to get things that are really wonky looking.
So if you knew which levels to concentrate on, you could actually do a few extra V cycles on some coarse level without increasing the overall work rate.
Sure, yeah, and in fact, to obtain these results, I didn't mention this, but for all the previous plots, I was just doing a single V cycle on every level as you go up the AMG hierarchy. Here I actually did 2. So I am doing a little bit more work on these fine levels where you're getting good interpolation accuracy, right?
Can you imagine any way where once you set things up, you could tell when you might need more V cycles?
Perhaps, yeah. I don't know of a way off the top of my head. I mean, of course, here I was cheating, right? Like this, I'm getting these interpolation error plots by, just plugging everything in and calculating, right? Because my problem size is small. I don't know of a way off the top of my head that you could sort of make a reasonable guess at how interpolation accuracy is doing on the fly. Yeah.
Scott,
Oh.
for this example, I mean, is this a decent AMG? Like, what is your V-cycle convergence rate for this course?
Oh, it's what you would expect. It's like 0.1, yeah, 0.1 convergence.
No different than if you had left interpolation alone?
Oh, I'm sorry, I think I misunderstood the question. You're saying when you mess with interpolation, what kind of convergence rates are you getting?
I was asking just simply if you take this course and you run a zero box, does it perform as well? Meaning, is this problem
So the funky coarsening but standard AMG interpolation, what kind of convergence factors? I believe they were similar to like 0.1. I would have to go back and run it to double check that, but as I recall, it was 0.1-ish.
Mark?
Have you thought about checking doing unstructured geometric multigrid? Especially on a test problem, it's kind of not too terribly difficult to do, where, say, randomly picking points and then remeshing, you're getting triangle or something, and remeshing, and then doing a geometric multigrid that would be with the Galerkin coarse grids and or even not Galerkin coarse grids. And that seems like the upper bound of what you could possibly do with AMG.
Sure, yeah.
And like I've seen super convergence where F cycles with that type of thing, the number of iterations required to get a constant reduction in residual went down as you scaled up, which is kind of non-intuitive for working in AMG, right? Which is the full multigrid effect.
Yeah.
But I've never quantified it by doing convergence studies. It'd be interesting to see whether in a model problem like this, but with unstructured,
Sure.
coarsening, whether you could actually recover FMG.
Yeah.
Any other questions? Well, let's thank all the speakers in this session.